division ring is called a field. Commutative division ring is called a field. That is a ring R with identity 1 not equal to 0 is called a field if R is commutative and every non-zero element of R is a unit. That means every non-zero element of R is the inverse of some non-zero elements. Okay, so if field is now, if you look at the structure which I sent you in last night in the WhatsApp group, and if you look at this structure properly, the direction of the movement, you will you'll be able to understand that why ring is the smallest structure and field is the largest structure, and how to reach from one algebraic structure to another algebraic structure. Why this word field is so important, why this definition field is so important, it's because if you can remember, in while studying vector space, probably you can remember that we considered the vector space V over the field F with the addition, with the vector addition and the scalar multiplication. And this triplet was called the vector space. The elements of the vector space were constructed by choosing the elements from the field. But there, we didn't learn the field in details. So field comes from ring. Field is another algebraic structure. The examples of fields are, there are many examples of field. Let me give you some examples. Say we can consider the ring of rational numbers is division ring and which is also field. Set of real numbers is division ring and is also field. Set of complex numbers is a division ring and is also field. But set of integers is not a field. Okay, every element is not an unit. Every element of is not unit of another element. So field is actually very important. Let us now solve the following example. Let R be the set consisting of the matrix of the following form: alpha beta minus beta bar and alpha bar. This element, this matrix is the element of the set M2C. M2C is the set of matrices of order 2 by 2 whose elements have been chosen from the complex number. And alpha bar, beta bar denote the conjugates of alpha beta. Okay, define addition plus and multiplication dot. In R by usual matrix addition and multiplication. Our objective is to show that to prove that R is a division ring, but not a field. So in the next page, we are going to prove this result. We are going to show that this set R, where operations of matrix operations and of addition and addition and multiplication, matrix multiplication have been considered. This is a division ring, but this is not a field. So let us try to prove this result. Okay, solution. First of all, we shall first of all try to show that the given set is a ring. Okay, this is the first task to do. So let us consider two matrices A and B, where capital A, the matrix capital A, is taken in the following manner, in the following form. Why am I choosing the element like this? Because keep in mind the structure of the element from this particular set is of the following form. B bar, beta bar is the complex conjugate of beta, alpha bar is the complex conjugate of alpha. And my second matrix is of the following. And we are choosing these two elements from the set R that has been defined in the question. Now, if I add these two matrices, if I add these matrices element wise, we get A plus R, I into B plus T, C plus U, I into D plus V, C plus U, I into D plus V, A plus R, minus I into B plus T. And obviously you see that this element is the complex conjugate of this element. This element is the complex conjugate of that element. So this type of element will definitely belong to the set R. It is easy to verify, and I'm not going to show it right now. It is easy to verify that A, B, if I consider the product of these two matrices, it will also take the form which is given in the set R. So AB will also belong to the ring R. I am leaving this verification for you. So verify this by yourself. Okay. Observe that the null matrix 0 definitely will belong to R, because 0 can be considered as the 0 can be considered, this element can be considered as the complex conjugate of this element. This element can be considered to be the complex conjugate of this element. 0 is the complex conjugate of itself. So 0, 0 will definitely belong to the set R. So 0 element belongs to the set R, and for any non-zero element or non-zero matrix in R, it is obvious that the negative of this element minus A will also belong to R, such that if I add these two matrices, the zero matrices will come out. Let us consider this zero matrix by the notation 0 bar. Okay. And further the distributive property will hold. So I'm asking all of you to verify this part by yourself. Is actually I'm leaving these two parts for you because this is just a kind of tedious calculation and some kind of some kind of adjustment has to be done to bring it into this particular form. So I'm actually, to save time, I'm actually leaving this particular calculations for you to do. So by these four things I have shown, I have shown that this the four properties actually are holding, the properties which are important for a structure to be ring, and therefore we can immediately say that the set R is a ring. Not only this, we also see that the identity element 1, 0, 0, 1, this identity element also belongs to R. Why? Because the identity element can be written in the following manner: 1 plus I0, and its conjugate is 1 minus I0, which is equal to 1. So this identity element is the element which is existing in the set R, and it is actually not equal to 0. Okay, so this ring is a ring with identity not equal to 0. So R is a ring with identity 1 not equal to 0, that is I not equal to 0 bar. So we have proved up to this. Next, let us choose two elements, I1 and -1 minus I, and also the elements 1I, I1 belonging to R. Okay, and we see that if I multiply these two elements, if I multiply the element this from by that from the left hand side, the resultant matrix will be I1, 1I, that is 2I. Next one will be I square minus 1 and 1 square 1, that is 0. This will be 0, and the next one will be minus 2I, which belongs to R. If I change the order of multiplication, and if I write like this, then what will I get? Let us try to find out. We get 0, 2, minus 2, 0. But you see that these two elements, this element and this element, they are not same. So this implies that the set R is a non-commutative ring with identity I not equal to 0. Okay, it's a non-commutative ring, remember. Now let us consider the element A plus IB, C plus ID, and C minus of C minus ID and A minus IB. Let us consider this element, and this element is a non-zero element. I'm choosing this element in such a manner that it is a non-zero element of R. Then if it is a non-zero element, then it implies that either A plus IB not equal to 0 or C plus ID not equal to 0 or both. Okay. In each case, in each of these case, the element will be non-zero element. That is, A square plus B square is not equal to 0, or C square plus D square is not equal to 0. And hence, A square plus B square plus C square plus D square is not equal to 0. If it is not equal to 0, let us give this element a name. Let us consider this element A square plus B square plus C square plus D square. Let us call this element by K. Okay. If I ask you to find the inverse of this element under this following condition, under the given condition, if I ask you to find the inverse of this element, you will find that we can find, and just before the class, I actually did this calculation for you, but I will ask you to verify this that I'm writing over here. If I have done any mistake in the calculation, you can later point me out. Okay, so to save time of this session, I have already calculated this inverse that I'm going to write. So we can find that 1 by K, A minus IB, C minus ID, C plus ID, and A plus IB, which belongs to R, is the inverse of A plus IB, C plus ID, C minus ID, and A minus IB belongs to R. But I am asking you to verify this because sometimes I do mistakes in doing calculations. So I'm asking all of you, whenever you find time, just verify that the inverse, this is coming as the inverse of the given non-zero element. Okay, verify this. I'm again and again repeating. It is my calculation, but verify this, whether it is true or false. Hence, after all this, what we have got, hence each non-zero element of R has an inverse in R, while R is a division ring, but as R is non-commutative, clearly R is not a field. Proved. So we have found that there exists an example where the set is a division ring but not a field. This set is also a kind of infinite set. This set, which is also an infinite set, you can construct the matrix in infinitely many ways. These were the examples where the set of rational numbers and set of real numbers, set of complex numbers, they were division ring as well as field. All of these sets are infinite sets, but also I have given you an example where the set is an infinite set, but it is a division ring, but not a field. I will suggest all of you to jot down all these definitions and theorems and uh, uh, results, corollaries in your copy properly, so that I'm asking all of you to memorize this result, because whenever we actually do the abstract algebra, we try to memorize the result. We the teachers, we also try to memorize the results. There are so many different and apparently similar results that sometimes we often become confused. I am not saying that abstract algebra is so easy. It is very difficult. I think abstract algebra is difficult. Uh, it's more difficult than linear algebra. It's my opinion is this. And the kind of freedom that I had while teaching you the principle of mathematical logic, this kind of freedom is not here. I'm not finding this kind of freedom in abstract algebra, because I mean to say that I am actually bounded by so many results. I cannot think in that direction or in this direction or in that direction. From every direction, actually, I'm bounded. And probably because of this reason, your performance in CA3 was not up to the mark, because you also are not actually finding this is so easy to grasp with. But ultimately, this topic is there in your syllabus. So I'm not going into the philosophical discussion of why abstract algebra is needed and this, then that. But since it is in the syllabus, so you have to cope up with it. And the way by which it can be done is to write down the results, the definitions, the theorems in a copy, one after another sequentially, starting from group till field. Write everything, and every day you just go through your note once. This is the definition, this is the thing. If you keep this practice, automatically the results will be set in your mind. And whenever in future the knowledge of this abstract algebra is required from your end, you can recall these things. Okay, so this is the only way to overcome these difficulties in abstract algebra. There is no other shortcut, sorry to say. Now here is an important result. The thing which I have done just now is a problem. This is not a theorem. But now I'm going to give you another theorem, and very important one. Theorem says any field is an integral domain. Any field is an integral domain. But the converse is not true always. Subsequently, we have another theorem which says that any finite integral domain is a field. Any finite integral domain is a field. So extra condition is there. It is finite. Okay. So a field is an integral domain, but not every integral domain is a field. But if you consider a finite integral domain, then it becomes a field. Okay. So I'm going to prove the first theorem. I'm going to prove that any field is an integral domain. In the definition of field, the word integral domain was not present. A commutative division ring is a field. We have mentioned nothing about the integral domain part. Okay. So integral domain part is actually a separate approach. Is on the, you just look at the picture which I sent you in the WhatsApp group, and the division ring part is on the other end. Okay. Now I'm going to prove that every field is actually an integral domain. Let R be a field. Let R be a field. And A comma B be two elements of R such that A not equal to 0 and AB is equal to 0. Okay. This part you can consider that this is the trick of the proof. In R, small a is a unit, because in field every element is unit, and hence A inverse exists in R. Then 0 can be expressed as, the element 0 is expressed as A inverse into 0. And in place of 0, you can put AB. So we can write it as A inverse into AB. Now associativity property holds. So we can write it as A inverse A into B. A inverse A means 1. So we can write 1 into B, and which is B. Thus, we find that R is a commutative ring with non-zero identity and without zero divisor. Divisors. Hence, R is an integral domain. Hence, R is an integral domain. Why is it so? We started with A not equal to 0, and we have come and since R is a field, R is actually a R is actually a every field is a commutative ring, because you know that commutative division ring is a field. So therefore R is a commutative ring. Okay. So since R is the field, R is a commutative ring, and since R is a field, identity element, non-zero identity element presents in R. We want to prove that to show that R is an integral domain, we need to show that zero divisors do not exist. When do the zero divisors exist? When A not equal to 0, B not equal to 0, but their product is 0, then we say that there are zero divisors. But if the product equal to 0 implies that one of the element is 0, then it is not a zero divisor. I started with A not equal to 0 and product is 0. And subsequently, I have shown that if A not equal to 0 and the product is 0, the other element B must be equal to 0. So obviously, such a situation is not a situation of existence of zero divisor. And therefore, R is a commutative ring with non-zero identity which has no zero divisor. And therefore, R is an integral domain. So first theorem has been proved. What about the second theorem? Any finite integral domain is a field. Let R be a finite integral domain. Finite integral domain. Suppose we are considering the R to be consisting of a finite elements, a set containing finite elements, n elements are there. Let A belongs to R. A is an element which belongs to R and A not equal to 0. and we consider the set. We consider the set, and you can say that this is another trick over here to prove this result. You have to proceed it in this manner. So we consider the set S, which has been constructed by considering the elements AA1, AA2, dot, 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 AAN. A is an element from R. So A can be either A1 or A2 or AN. A is an element which is from the set of elements which are present in R, which is the element from the set R. Okay. Now it is obvious that this set capital S is a subset of R. Since R is closed under product, since R is a ring, so it has to hold the closure property. Now, if AAI, this element, and AAJ, this element, they are same, where I and J, they lie between 0 and N, then cancellation property will hold. Now I am trying to use the properties which I actually left for you to prove. So from there we can say that AI equal to AJ, as A not equal to 0, which implies that elements of S are distinct. To quickly take the screenshot of this page, I'm going to the next page. Okay. Then, since S is equal to R, no, not since, then as S is subset of R and the cardinality of the set S is same as the cardinality of the ring R, so we have S is equal to R. Now, since R contains 1, we have for some J, where J lies between AAJ is equal to 1, which implies A is a unit. And since this happens for every non-zero element A of R, we have R is a field. So this completes our proof that every finite integral domain is a field. So the property, that cancellation property, which I didn't prove over here, probably we are thinking that this cancellation property is actually not required. It's just that's just a theorem which we can avoid to prove, but this is not the case. Everything is related to every other subsequent things. Everything is related to every preceding things. So it's this type of topics actually move very sequentially, and you never know in which type of problems which is going to help you out. Now, it is not the only way by which this can be proved. Other ways may be there, but you have to always find out the optimum way by which the problem can be dealt with. And right now I can think of this way of taking the help of this cancellation property to help me out to solve this particular problem. Now, I'm going to conclude my today's session at this point. Tomorrow we are going to meet once again, and we are going to do some more things about this ring theory. Tomorrow I'm going to conclude this the topic of ring theory, discussion of ring theory and field and etc. And in the next week I'm going to take the classes on Boolean algebra, which is very important for computer science point of view. And after that, from next to next week, I'm going to start the graph theory. The graph theory's note has already been shared with you. You just go through the note. I will quickly go through the sections, and we'll do some problems on the graph theory in the class. Okay. So with this, I'm going to conclude, and the results which I have asked you to prove by yourself, just don't, um, don't miss. You are not actually studying properly. You are in this online session. Actually, you are doing some. I mean, properly the study is not proper. Study is not being done by you. It's you are just um, wasting your time. So do not do this. In the long run, if you do in the long run, you will be in trouble. In the long run, I'm saying. So please study. Don't stop studying. This is the thing which I in the beginning of today's class I told. In the end of this session, I'm again telling you, please do not stop studying. The future is not clear to all of us. What is going to happen? At any point of time, suppose you are in a company, you are doing your jobs, that time you may be, once again, you may be assessed with all of your knowledges that you have gathered in BTech. Maybe your company is asking that in your, say, when you were actually, when you actually passed out, that time the situation was online, you are not properly tested. So if you want to have some promotion, we will take another assessment for you. Education policy keeps on changing, remember. And so is the job policy also. So please do not stop studying. With this, I'm going to conclude my today's session. See you tomorrow. Till then, bye.